Okay. That doesn't look right. That should have said something different, but that's okay. So now we've already seen before we had an equation or inequality and you were given a value for one variable, how we could check to see whether it was a solution. We plugged it in. If it led to a true statement, it was a solution. If it led to a false statement, it wasn't a solution. Well, now we have equations in two variables. So if you're going to check to see if something is a solution, it's going to be something with two values, a point. Right? So how would I check to see whether any of these points would satisfy this equation in two variables?
Plug in each of the things.
You just plug them in. It's just like one more thing to plug in. So see if you could find out which one of those is a solution. Which one of those points would satisfy that. I'll call it for right now a function rule. Drew, you get an answer?
Yeah.
What'd you say? B? How many said B?
I'm not even done.
Keep going. They might be wrong. Anybody get a different one?
I read the whole thing.
Everybody said B? Okay. So let's see. Let's do A and B, just to show. All right, so for A,
Yeah, that's right.
for A, we have to plug in 3 times 3 minus 4 equals 7. And that's a question mark, right? We don't know that. 9 minus 4 equals 7, question mark. 5 equals 7. And the answer is no. So that's not a solution. B, 3 times 1 minus negative 4 equals 7. Check. So that's 3 plus 4 equals 7. And 7 equals 7. Okay, here you go. What property tells us that 7 equals 7? Reflexive property. So when I can speak better, because I don't want to go through this stuff speaking like this, but going over the results of our 9-week test, we did the properties questions we didn't do well on at all, and especially the one question that had to do with this one thing we missed. I think that was the most missed question of all, and we talked about this over and over and over again, and it was a symmetric problem, and you got it mixed up with reflexive again. So the reflexive is the thing that says that a number equals itself, as if we needed a property to tell us that, but they do expect that. So the answer here was B. Okay. So you try this one now. See whether that is a solution. Okay, how many say yes? Solution. Sebastian, Micah, Drew. Anybody want to jump on the bandwagon? How many said no? Ooh, this was an election. You were outvoted, right? So the consensus is it's not a solution. Let's plug it in. Right, it'll be 4 plus 2 times negative 1/2 equals 5. Question mark. 4 plus, what's 2 times negative 1/2? Negative 1 equals 5. For those who thought that it was a solution, what did they probably do wrong? Forgot the negative, right? So you had 4 plus 1, and it looked like it was a solution, but it was actually 3 equals 5, which is not true, so not solution. Okay. So any equation with 2 variables, and usually it'll be x and y, but it could be other things like number of Texas congressmen versus years, maybe you'd use something other than that, but usually it's x and y, can be graphed by plotting points and connecting the points with a line. You make it, generally this is like the starting point, and we use this even in Algebra 2, even in pre-calculus or math analysis. The first thing you do when you don't know anything about a function at all is you make a table of values and plot some points and look at them on the graph, see what it looks like. Because if you don't know what it looks like at all, I mean, where else are you going to start other than, okay, let's see what it looks like. Make a table of values. So this is usually the starting point. Right? Table of values looks like that. Right? Now, these values here, the x values, you got to start somewhere. I mean, just drawing those lines on a piece of paper and labeling x and y doesn't get you started. You've got to fill these in with numbers, right? And where do you get those numbers? You choose, right? Those are the independent variable. They're the ones that you can pick which ones you want to graph. You can pick how many points you want to graph. You can pick what values they are. So you choose, right? Sometimes in the book, if they're showing us that they made a table of values, it won't be clear where did they get their x values. Just understand they get to choose that. So they might have chosen some other values unless they were told which values to choose. So that's a common question. Where do they get the x values? They chose them. They get to choose them. Independent variable, right? So once you've filled in some numbers here, then if you got an equation with 2 variables, you can plug in for one of the variables, you can calculate the other variable. So you calculate the y values, you plot the points. Now, since this is an equation that we're graphing, and since we could have picked 3 points, 10 points, 100 points for this, we're going to connect those points with a line. It doesn't just represent those points we chose to graph. It represents any point we might have chose to graph. Right, so definitely now we're at the point of connect those points with a line. Right? So when you're given a limited domain and said find the range, then you just get a limited set of points. But if you're not given points, if you get to choose, that means it's like an infinity of points. Connect them with a line. So, graph. Now, you could see I started a table of values here, and I chose -2 to 2. I think in the book, in their example, they chose -2 to 2. Okay, now, let's say that I need to find the y value that goes with x equals -2. Then I'm going to come over here, and I'm going to say -2 times -2 plus y equals -3. So 4 plus y equals -3. Subtract 4, subtract 4. Y equals -7. So now I can fill this in. So I would have to go through that process 5 times to make my values. Now, here's really what you would do. Okay, that you could do that. But to make things easier, it's better to solve that equation for y before you start, because then you won't have to do all that solving every time when you're finding the y values. Solve the equation for y. That's why in that section where we were solving literal equations, equations with more than one variable, we had to do this kind of thing. Because you will have to do that kind of thing. There will be times you're given it in this form and you really would like it solved for y, because that's the function form. So better, right? Better would be solve it for y like I did there first, and now plug in the values. It'll be less solving for every value that you plug in, right? So now I can plug in y equals 2 times negative 2 minus 3, negative 4 minus 3, negative 7. Y equals 2 times negative 1 minus 3, negative 2 minus 3, negative 5. Y equals 2 times 0 minus 3, which is 0 minus 3, which is negative 3. Okay, y equals 2 times 1 minus 3, which is 2 minus 3, negative 1. And then y equals 2 times 2 minus 3, which is 4 minus 3, which is 1. Okay. Okay, let me do something here, because I didn't do that very well. Let me see if I can grab our table of values. Good. Edit, copy, and insert page. Edit, paste. Good. Now we can graph it. Right. So our values, it looks like our x values go from negative 2 to 2. So I definitely want to have my, make sure I've got some space on the left side of the y-axis and some on the right. My y values start kind of low at negative 7 and get up to 1. So I would probably draw something like this. Right, that'll allow my x values to go from negative 2 to positive 2. And I'll let my y values go. That's a 1, 2, 3, 4, 5, 6, 7, down to negative 7. X and y. That's terrible. Okay, so graph the points. Negative 2, negative 7. Negative 1, negative 5. 0, negative 3. 1, negative 1. And 2, 1. Okay, so we made our table of values. We chose x values, or I chose x values. I calculated the y values, and now I plotted the points. And now, because this is actually an equation, what do? Connect them with a line, right? That represents not just those 5 points that I picked, but any point I might have picked. And how many points could I have picked? Infinities. How many points are on a line? Infinity, right? Keep straight. I mean, we're going to get to, I don't think we're going to talk like this today. We'll talk about it next class for sure. But how many points do you need to determine a line? Just 2, right? But how many points are on that line? Infinite. Infinite, right? A continuous line on a graph is made up of infinite points. I mean, these are very, in a way, these are really, really sophisticated topics here, right? The idea that 2 points, that 2 points uniquely determine a line, that goes back to what are called Euclid's 5 postulates, right? Which is, Euclid is one of the most famous mathematicians of all time, an ancient Greek, a guy who tried to put a framework around all kind of mathematical knowledge, right? And the thing that was at the heart of it is, you don't want to accept anything as truth unless you can prove it, okay? And the fact is, you got to start somewhere. There's got to be something that you absolutely know is a true thing, right? And so is the things that you accept as being true, even though you can't prove them, kind of like religion, right? Those are called postulates or axioms. The things that then you will try to prove after you've assumed a few things are absolutely true, those are called theorems. So you don't want to have many axioms, things that you're just accepting to be true without proving it. So there were 5. he said there was 5 things, and one of them was basically that, given any 2 points, there is only one straight line that could go through those. Or actually, I should say one line that goes through those. Now, what's kind of interesting about that is that the 5th postulate was one that even Euclid, when he made it, didn't think that it necessarily was a postulate, that maybe it could be proven to be true using the other 4. The 5th postulate said that if you have a line and a point that's not on the line, then it should be that you can draw, that there would only be one line that goes through the point and is parallel to the other line. And to us, when we look at it, we think, that sounds reasonable, You've got a line and a point, that there might be only one line that could go through that point and be parallel to the given line. It seems like it makes sense. But because he wasn't sure, for like 2,000 years, people tried to prove, using the other 4, that this was true. And they couldn't do it. They couldn't do it at all. Until the 1800s. And then a guy, probably an even more famous mathematician named Gauss, came along. And he didn't prove that it was true. He proved that it's not necessarily true. So he came up with a whole different framework for geometry that became known as non-Euclidean geometry. And that is the thing. I know you've heard about the theory of relativity. You probably don't know what it is, but that was something invented by Einstein in 1905 and 1915. There was 2 different ones. But he took calculus that was invented by Newton in around 1700 and then used a non-Euclidean frame of geometry and came up with the theory of relativity, the thing that is the heart of the nuclear bombs and things like that. So, you might not be able to imagine in your mind how could you have another line that goes through that point and is parallel to that line. It's kind of bizarro kind of thinking, but you know what? That's what mathematicians at a really high level, that's what they do. That's all that they do. They do almost none of what we do here. Okay? They're always trying to prove things true that weren't proven true before. And so this idea that only you need 2 points, you can uniquely determine that line, that is true for Euclidean geometry, but that is, after all, what we're doing right now. And, okay. Sorry, I digress. I find that stuff kind of interesting, though. So you try to do the same thing. Try to make a table of values, and you probably want to solve this for y before you start calculating your y values, and then make a graph. Okay. Exactly. I would have started by doing that before you do anything. You're not going to get away without solving for a variable. At least 2. I mean, we saw really complicated formulas when we do literal equations, but this is not that complicated. You got these values. You get those, Drew? Everybody get them? Katie? I mean, just plug them in one at a time. You're going to learn some things here within the next couple lessons. Now, actually, be more like in the next unit, where we learn that this is a straight line, right? That slope-intercept formula is a straight line. And there's easier ways to graph it than having to plot 5 points. But at this point, all we're doing is saying, okay, not knowing anything about it at all, let's make a table of values and see what it looks like. So then you make a graph, right? And you make sure when you look at the numbers before you do it, so you could draw an appropriate graph. you know, my x values are symmetric with respect to the middle, right? -2 to +2. That's easy. But my y values, it looks like it needs to go a little farther down than it does up. So I would probably draw it like, draw the x-axis maybe like that. And then I'm going to label them every 2. 2, 4. -2, -4, -6, -8. And there's a -1, -2, and 1 and 2. That is x, and that is y. Plot points. -2, +4. -1, 1. 0, -2. 1, -5. 2, -8. Does that look good? And I'm going to draw a line. Connect them with a line. Not a very good line, but close enough for government work, as they say. So, now we learn that when you have a graph that it looks like the lines all fall on one straight line, that is called linear. Right? Linear. Linear equations means that the graph is a straight line. Now, that's the thing that's missing from all this Euclid's postulates. He never said it was a straight line. So people conceived of like different systems where things aren't necessarily straight but parallel. But in our case, when we say, you know, it's not we will use the word line can mean different things. It can mean curved lines. We will deal with curved lines eventually in math, but we mean straight line. I'm going to stay more over here because the microphone is only working here and I'm not speaking very loud. The standard form of a linear equation is that. It can have an x term, it can have a y term, and it can have a constant term. Right? That's the ax plus by equals c. The a, b, and c are real numbers. They're just numbers of some kind. We may not know what they are before we start, but they are real numbers. You know when you're looking at an equation like that it's linear because the x and y terms, the x and the y, are raised to the first power. Right? How do you know that this x and this y are raised to the first power? Because when you don't see an exponent, what is it? It's 1, right? So whenever you see an equation where the x and the y terms are raised to the first power, you know you're dealing with a straight line. Okay? It's linear. And remember, we said this already, but now bringing back in that word domain, right? That the line is not made up of just those points that we used. It's made up of an infinity of points. Okay, so now we still are going to be talking about this concept of domain, right? And what do we mean by domain? The set of the inputs. But in this case, the inputs are x, right? So it's the set of the x values. But if there's an infinity of x values, how do you write the domain? Not by making a list. You can't make a list of infinity of points. So that's where this starts to get a little more complicated. And I'm not sure how deep they go into this in Algebra 1. The textbook has this in here, and I can just say this is a concept that our students struggle with every year. So it's not a bad thing to introduce it anyways now. So domain now is going to go from being a finite set of points to being an infinity of points. But we know how to describe them. You have the tools to describe them. You may not realize it, but you do. Okay, so given the standard form, what if A or B is 0. Right? If A is 0, then 0 times x is 0. So you wouldn't have an x term. Or if B is 0, you wouldn't have a y term. So then you're just going to get equations which are x equals a constant or y equals a constant. Are we really that far on there? Sure, anybody's... There's a couple of people writing. You know, because yesterday, so I was starting to lose my voice on Tuesday. I knew it, okay? My wife had been sick last week. I mean, really, she seemed really sick, but she's tough. She still ran every morning, went to work every day. Oh, she's really crazy. So she was starting to get better, but I felt fine, right? Monday morning, which is a B day, I just started to feel this little tickle. I'm like, crap, I know what this is going to be, you know? So I ran out and bought some cold medicine because sometimes you can head these things off before they start to really like drain in your throat and all that. And I got something, but it didn't help at all. I could tell Tuesday, this is going to get bad. But I thought, okay, Wednesday, you guys don't have school, so I don't have to teach. So that's good. If I can just make it through Tuesday, I'll be fine. And then, so Tuesday, I mean, during the day, it just got worse and worse and worse. But I was able to teach the lessons to Algebra 1 and then Algebra 2 trig. And then Wednesday, we had like training stuff, but they let me go home early anyways. And then I thought Thursday, you know what? I'll just show them the videos because I had made the videos with you on Tuesday. So yesterday, my 3B, they listened to us. Some of it was like they could hear me talking to you. They could hear me talking to Portia. You know, that's what you get. To me, it was like kind of slow. But like now, you know, when you pause to let somebody you see taking notes, it does slow things down a little bit. But it worked. It helped because I had that. And today, I mean, all night I sat there going, golly, am I going to be able to talk enough tomorrow? Because I don't have a video now. Okay, so now we need to discuss what kind of lines are you graphing when you either have x equals a constant or y equals a constant. Because another thing that we make mistakes with all the time. So we're going to graph the line y equals 2. Now, is that a standard form of a line? Sure. I mean, if you compare it to the ax plus by equals c, sure, it is. What is the value of a? If it's 0, that's why you don't see the x, right? Our a is 0. And what is our b?
2.
Nope. B is the coefficient of y. If you don't see a coefficient, what is it? It's 1, right? And our c is 2. The constant on the other side is 2. So this is a standard form of equation of a line, y equals 2. But we know that for every point I graph, the y coordinate is going to be 2. So again, we can pick x values to put in there. And let me just pick, I don't know why I chose that. -2, -1, 0, 1, and 2. And graph those 5 points. Right? There's nothing for me to plug in here, right? You don't see an x. So there's nothing to plug in. Y equals 2, period. End of story, right? So I graph these 5 points. -2, 2. -1, 2. 0, 2. 1, 2. 2, 2. Okay, do we see the shape? Yeah. We will. We will. I mean, this is the function rule is y equals 2. So do we see enough of a shape to connect all those with a line? Sure. Sure, I think so. So let me do that. Now here's the $64,000 question. I can't get it anyways. What kind of line is that?
A linear.
No.
Straight line.
No.
What the?
What do you call a line which is flat like that? It's horizontal line, right? You got to know what's a horizontal line and what's a vertical line. This is the horizontal.
I thought it would be. Oh, okay.
I mean, look, when we were doing on the homework from last night, when we did, how can you tell whether this graph is a function? We did a vertical line test. Vertical lines go up and down. Horizontal lines go left and right. You know, many years ago, I was teaching Algebra 2 back at Kickitan, and I had a big auditorium kind of seating classroom, and I said, okay, what kind of a line is horizontal? And, you know, the kids were going to do either this or like this. I'm telling you, half of them were doing this and half of them were doing that. And let's see, you only had two answers. If you guessed, you would expect 50% to get it right. And I was getting about 50% right. So most kids there were kind of guessing about what's horizontal and what's vertical. And you really need to know that. I mean, I don't know what it is that would relate that to you, but the horizon, you know, the horizon is like this. I don't know if you got skateboarders that do verts or something like that, okay? But you got to keep straight. What's horizontal? What's vertical? And more than that, you got to understand that the horizontal line is when it's y equals a constant, okay? X equals a constant is not going to be horizontal. What's it going to be? It'll be the vertical. Those two things you got to keep straight. What's a horizontal line? What's a vertical line? Okay. Okay. That was a bad one, but okay, too late. So now we go to the x equals a constant, right? X equals -1, which means I don't get to choose the x values anymore. They're all -1. Okay, now in this equation here, there is no y to calculate. So basically, it's going to be -1 no matter what the y value is, which means I'm just going to put in some values. How about -2, -1, 0, 1, and 2?
Wait, so you get to pick the values if there is no y in like the
Yeah, in
whole
this
thing?
special case, you can pick it. So now I plot those points. -1, -2. -1, -1. -1, 0. -1, 1. -1, 2. Okay, again, we see the shape. We connect it with a line. It's a little better. And what kind of a line is it? Vertical line. So vertical line is when x is the constant. Y can be anything, but x is fixed. Horizontal line is when y is the constant and x can be anything. I know you've had a little bit of this before, you know, but a lot of this leads to a lot of confusions. You know, we're going to get into the concept of slope. What's the slope of a horizontal line? What's the slope of a vertical line? Well, it causes a lot of confusion. Don't like it. Come on, Katie.
There's too many like forms, so like standard forms, like it's like I don't know some other stuff.
Yeah, we're going to do that. That's true. Okay.
I don't think the Y1 and the Y2 or something like that.
I got all the forms. My prof, that was my problem.
Okay. Well, we do have to deal with most of those forms. It's just part of it. So this just kind of summarizes horizontal, vertical lines, right? Horizontal line is y equals a constant. Vertical line is x equals a constant. So a lot of times we'll do more of this for many lessons to come. But for example, on a test, I might say graph x equals 3. And this is what I get on the test, right? Students will do like this, 1, 2, 3, and they may just make a point. Done. But it's an equation, x equals 3. It means every point that has an x coordinate of 3, that's what you're drawing, right? So it's actually up and down. So that could be the starting point. Put in the x equals 3, the point. But then make sure you draw the line. It's not just one point. So here's your U-try. Graph y equals 2.5, graph x equals -4. Okay. How can we say this? Which one? Just show me with your hand, right? The first one, which direction did it go? And the second one?
Hiya.
Yeah. Karate chop. Karate chop, right? So y equals 2.5, right? It means it's got every point on this line is 2.5. X equals -4. Ah, that's terrible. Close enough. So we get it, horizontal, vertical lines. Y equals a constant, x equals a constant. If you can remember that, believe me, it'll pay off many, many, many times over. So, answer these questions, right? Is a horizontal line a function?
Yeah.
I mean, let's go back to this slide right here.
Yeah, it
Is that a function? Does it pass a vertical line test?
will.
It does, right? So you would say, yes, that's a function. What about a vertical line?
Nope.
I mean, does a vertical line pass a vertical line test? No. How many points are on that? Does it intersect with?
Infinity.
Infinite, right? There's infinitely many points on the line. So when you draw a vertical line, you intersect infinitely many times. Oh, that reminded me of another thing. But so we have to say here, right? Is a horizontal line a function? Yes. Now, I didn't put out the calculators today, but you remember the face of the calculator good enough. Come on. Remember when we entered an equation in the calculator, it's with this y equals button right there. So can you enter y equals a constant, a horizontal line in the calculator?
Yes.
Sure.
Yeah.
Right? I can go to that calculator and I can say, I'm going to clear my memory. How do I clear memory again?
Second plus.
Second
plus
plus
2.
7, 1, 2. Enter. And now I'm going to come up here. I'm going to put my y equals 2.5. And I look at the graph. And there's my graph. That's a function, passes the vertical line test. Okay, how about the vertical line? We already said the vertical line is not a function. You know, you don't have an x equals button on the calculator. That's why you can't enter it in. There's no way for you to enter a vertical line because it's not a function, and we're only dealing with functions. Okay, now here's another question. For example, y equals -3. 1, 2, no, y equals 3. What's the domain of that? How would you describe the x values that make up that line? Well, you know, is there a limit to how many x values are on that line?
No, infinite.
It's infinite. So just like we had this when we were solving inequalities sometimes, even when we solved equations, there were times when the solution was all real numbers. So the domain here is all real numbers. Okay, now x equals negative 6. What is the domain?
All real.
So,
Wait.
okay, what are the, again, now all we have to state is what are the x values of every point on that line? Negative 6, that's the domain. Right? This one has a domain of, the set of values is negative 6. There are no other x values on that. What is the range of y equals 3?
3.
Just the 3, right? It's the only y value on there is 3. Okay, what is the range of x equals negative 6? All real numbers, up and down, right? So it says graph the function negative 1/2 x plus 4 with a domain of x greater than or equal to 0. Okay, so this is the first time we're seeing that. When they give us an equation, they're actually giving us a domain to use. So now we can't choose any x values. We have to choose x values that are in the domain. Okay, so let's pick 0. I'm just going to pick 0, 1, and 2, just to shorten this up. 0, 1, and 2. So plug these in to calculate the y's. What is, when x is 0, y is 4. When x is 1, y is negative 1/2 times 1 plus 4. 3.5, right? And what about 2? It should be 3. Right? 2 times negative 1/2 is negative 1. Negative 1 plus 4 is 3. So I graphed those 3 points. 4, 1, 3.5. 2, 3. Okay, then what do we say we're going to do? We're going to connect them with a line, right? But that line, we know that we know where it starts, right? It starts here, but it goes infinitely down like this. And that probably doesn't do it justice, but it does have an arrow right there, right? That goes infinitely down. So how can we describe the range, the set of y values? We know that x values are x greater than or equal to 0, right? Because it's to the right only. But how do you describe the set of y values that start here and go down? Remember, this is negative, this is positive 4. Use an inequality. Less than or equal to 4, right? So the range would be y is less than or equal to 4. Right? There's an infinity of points, so if you want to describe it, you're not going to be able to give it like a set of values. You have to give a range, use an inequality, which implies infinitely many points. Right? There's no y's above 4, and then the arrow goes infinitely down, so y less than or equal to 4. My guess, this is a harder concept to get a hold of, but it's part of math. What can I say? So you try. Graph this function. And you could see on the scale here, I don't know, why did I do that? I think I used the values because I wasn't being lazy yet. Oh, because it said x is less than or equal to 0. So I think I used negative 5. Yeah. I think I used negative 5, negative 4, negative 3, negative 2, negative 1, and 0. So plug those in here, Make your y values graph. See if you can come up with the shape and the range. That's what you should be coming up with. Right, that much of it we've been doing. That's been what's different about this now is this limited domain, limited range thing. So if you come up with this graph, you can see that the domain, the x values start here, and they only go to the left. So x is less than or equal to 0. How would you describe the range? It starts here, that's an endpoint in that line, and only goes up from there. Yeah, I mean, greater than or equal to 1. So the range y greater than or equal to 1. Okay, let's see. So the distance d in miles that a runner travels is given by the function d equals 6t, where t is the time in hours spent running. Okay, the runner plans to go for a 1.5 hour run. Graph the function and identify the domain and range. Okay, so let's see. Make a table of values. Time is the input, distance is the output. What is going to be the domain? I mean, they've told us that he's running 1.5, right? So we don't need this thing to go beyond t equals 1.5. How low should it go? Should there be negative values of t? Would it make any sense in the context of the problem to have a negative time that you ran? No. So in fact, we know that we're going to go 0 is the first number, and that 1.5 could be the last. How about if we just put in 0.5 and 1 and 1.5? And now we'll use this d equals 6t to calculate the d's. So when t is 0, d is, when you haven't run for any time, you haven't gone any distance. When you've run for 1/2 an hour, 6 times 0.5 is 3. When you've run for 1 hour, 6 times 1 is 6. And when you run for 1.5, 9. So if we graph the function, right, 0, 0.5, 1, 1.5, and this is going up 3, 6, 9. Okay, 0.5, 1, 1.5. Then we have these points, 0, 0, 0.53, 1, 6, and 1.5, 9. And should we connect those with a line?
Yeah.
Sure. I mean, it includes all the points in between. So now what do we say is the domain? Meaning what are the values in between here and here? How could you describe that with inequalities?
0 is greater than or equal to. Wait.
Is 0. Say again.
X is greater than or equal to 0.
Okay, what else? What about on the right side? Okay, well, we had a thing we used for those kinds of inequalities, remember? 3-part inequality. 0 less than or equal to t less than or equal to 1.5. And this is where you always see 3-part inequalities. When you're doing domain and range, it comes up all the time. Okay, what's the range? Do the same kind of thing now to give us the range of y values. 0
Is
greater than or equal to? Less than or equal to. Right, it's the least of it. Everything is above 0. So 0 is less than d, which is less than 9. Right? I mean, think of the variable that's in the middle. You always think of the variable as like the shading, right? So the shading is, 0 is to the left of the shading, and the shading is to the left of 1.5. It's in between those two. And here it's in between 0 on the bottom and 9 on the top. Those are the values you want. So how fast is this guy running? Come on, you can figure it out. 6 miles per hour. How many minutes per mile if he's run 6? 10. Yep. That's blazing. Blazing, right? So what if it said, what if we adjust this to say he's going to run 12 miles? They didn't tell us the time, but they told us the, yeah. When I finish this. Right? So now we can make our same table of values, right? It's T and D. And it can start at 0, 0, but it's actually going to go all the way to 12. So if D equals 6T, how am I going to find the T that's associated with that? If D equals 12, how do I use this to solve for T? Plug in the 12 right there. 12 equals 6T. T equals 12 over 6, which is 2. So we could have added a point to our table of values that we already had. But how would it have changed the domain and range? What's the domain now if it starts at 0 and ends at 2? Use a 3-part inequality. 0 less than or equal to T less than or equal to 2. How about the range? 0 D less than or equal to 12. Okay. That's enough. I give. So that is not the right thing. That's okay. Of course you got homework. Don't have homework. That's sacrilege.